So our first order of business is the Richtmyer Memorial Lecture Award, and this year's Richtmyer Memorial Lecture Award is presented to Professor Sir Michael Victory Berry in recognition of outstanding contributions to physics and effectively communicating the contributions to physics educators. Sir Michael Berry is a world-renowned theoretical physicist who is famous for his discovery of geometric phase effects, i.e. the Berry's phase, in quantum mechanics. His more than 450, I'm actually reading that right, scientific publications cover topics ranging from glaciers to nonlinear dynamics to optical diffraction, quantum mechanics, and caustics. He is also author of Principles of Cosmology and Gravitation, with a well-deserved reputation for polished, elegant, and illuminating lectures. He has brought the excitement of contemporary theoretical physics to audiences around the world. And I can add my personal testimony that he wowed the SPS students last night. Regarding his election for this award, Berry said, "I am delighted to receive this unexpected honor from the AAPT and humbled to be in the company of such distinguished previous recipients." Berry is the Melville Wills Professor of Physics Emeritus at the University of Bristol. He holds a Bachelor of Science degree in Physics from the University of Exeter and a PhD in Theoretical Physics from the University of St. Andrews. He holds 10 honorary doctorates and 1 honorary professorship. His career developed at the University of Bristol, first as a postdoctoral fellow, then lecturer, then reader, before becoming professor in 1979. From 2006 to 2012, he was editor of the journal Proceedings of the Royal Society. We've heard of that one. His recognition with the Maxwell Medal and the Prize of the Institute of Physics in 1978 was followed by numerous other science and mathematics awards, including the Ig Nobel Prize, which he elaborated on for the SPS students in 2000, sharing the prize with Andrew Geim for their work on the physics of flying frogs. Berry was elected to the Royal Society of London in 1982, elected a foreign member of the National Academy of Science of the United States in 1995, and knighted by Queen Elizabeth in 1986. Berry specializes in semi-classical physics, asymptotic physics, quantum chaos, applied to wave phenomena in quantum mechanics and other areas such as optics. He has given many prestigious lectures and held visiting positions in Nigeria, Italy, Germany, the Netherlands, Switzerland, France, Australia, New Zealand, the United States, Israel, Mexico, and Belgium. So clearly a world-renowned scholar. I'll ask you all to join me in welcoming Sir Michael Berry.
Great.
Oh dear, okay. The Richtmyer Memorial Lecture awardee receives a plaque, which I'm supposed to hold this way, and also a check with which I was not entrusted, and gives the lecture we're about to hear. So I think we're supposed to smile for the cameras.
Thank you.
Have we got it?
Very good. Well, thank you very much.
Thank you.
Thank you indeed. Well, I'm tempted to say after this lovely introduction, as a colleague of mine once said, you've heard the hype, now you're going to get the lope. I am delighted, of course, to be honored in this way by the American Association of Physics Teachers. I'm considerably humbled, as was mentioned already, by the list of previous recipients and, of course, by the name Richtmyer. I never met Richtmyer, but as an undergraduate, his book with Kennard and Lauritsen, many of you may know it, played an important part in contributing to my physics education. I'm also slightly embarrassed receiving this award because although I spent the first 2.5 decades of my nearly half-century as a physicist as a regular university teacher, for the second half I was a research professor without any teaching or administrative responsibilities. An envious host once introduced me when I was giving a lecture as the professor with no known duties. Yeah. But I do love to talk about physics as well as doing it. And today I'm going to tell you things that you surely already know, but maybe in ways that you might be less familiar with. Well, the underlying theme is connections. Now, there's this famous literary phrase, "only connect," by E.M. Forster, but many people in many walks of life have made the same point, encouraging connections, and I've heard it already at this meeting several times. My colleague, Sir Charles Frank, my former late colleague, in his retirement speech, he made this wonderful announcement: physics is not just concerning the nature of things. It concerns the connections between the natures of different things. That's a very deep statement and very true. Now, my connections are going to be some that link physics, not only with other physics, but with matters outside physics. Now, over the years, I've accumulated a number of bees in my bonnet. I checked that this English phrase is also known on this side of the Atlantic. And I'm going to use this occasion to release a few of them, and I hope that they're stingless bees. Okay. Well, let's start with the example in the title, the compact disc player. That was invented in 1982. And you know what it is. It's a 4-mile spiral of music in which the music is coded as a series of bumps and pits, microns in some dimensions and nanometers in other dimensions, coding, sampling the sound as a series of zeros and ones. Here is about 1,000th of a second's worth of, it's sampled 44,100 times every second. This would represent a 1 kilohertz note. Okay. Now, at the heart of the compact disc player, as you all know, is a laser. Now, that was invented in 1958. It scans the surface and reflects the bumps and pits as the disc turns, and then this on-off signal is transformed first into electricity and then into sound. Now, underlying the laser is a central principle of physics discovered by Einstein in 1917. Here he is around that time. And this was during the 2 decades of bewilderment that eventually led to the full uncovering of quantum mechanics, the world of quantum physics. Now, there were puzzling experiments concerning matter and light, and Einstein was thinking about how the two are related. Now, he already knew from Niels Bohr that in microscopic objects, atoms and molecules and so on, their states have energies that form discrete values. They're quantized. That's, of course, the basis of the name of our subject, quantum physics. We celebrated the centenary of Niels Bohr's discovery just last year. Now, Einstein also knew that not only material things, but also light has this granularity. Later, it was called the photon nature of light. And that, too, was very mysterious in the older physics where light was firmly shown. It was thought to be waves of electromagnetism. Now, what came to him in 1917 was an insight which still seems miraculous. It was while he was groping towards the full quantum physics, which didn't come for nearly another decade. And this insight was that these ideas of light and matter could be made consistent only if there were 3 processes by which atoms can absorb and emit light. Now, an atom can absorb light that shines on it and get excited to a higher level. There's no surprise there. And once excited, the atom can emit light spontaneously by decaying to a lower level. Now, Einstein recognized the need for this randomness. Essentially, it was incorporated fully into quantum physics some years later by Max Born, but he didn't like it then or afterwards, and he wrote already in 1917 The weakness of the theory lies in the fact that it leaves the duration and direction of the elementary processes, that's emitting light, to chance according to the present state of the theory. And still that's true now in 2013. And that spontaneous emission was the second process. But the true originality of Einstein was to realize that you need a third process for consistency. And that's stimulated emission, and it's the central principle underlying the laser. And that says that an atom will emit light in a way that depends on how much light is shining on it already. That was a new process, this stimulated emission. Now, it led directly to the laser, albeit 40 years later, in which an atom is pumped up to an excited state, and when a photon passes by, it stimulates the emission of another one, and you get this cascade in coherent form, eventually leading, after increasing intensity, to this pure, bright beam that we're all familiar with in a laser. So I've even got a better one here. Let me look at a better presenter. Yes, where is it? Where is it? Oh, there we are. Right. Now, here's the point which I want to emphasize. It was unimaginable in 1917 by Einstein that his quantum physics ideas would lead to the invention of the laser. Okay. The people in 1958 who invented it were different sorts of people with different kinds of imagination and talents. They were also experimentalists. And in turn, it was unimaginable to them in 1958 that in 1982, engineers would use the laser in the compact disc player. Again, it's a different, more practical mentality. I remember learning about the laser in the 1960s. It was described as an invention looking for an application. Okay. Now, of course, it isn't only physics that's involved with this unanticipated connectedness. You need, of course, mechanical engineering of very high order to get the disk spinning and so on. You need mathematics. It's quite subtle to encode the music as bumps and pits in a way that's robust against dust and scratches. It involves electrical engineering to convert the signal. It involves business. You need finance. You need to develop the machinery. You need advertising. Of course, you need the music that you're going to actually use this device to present. It's connections, connections, connections all the time. But fundamentally, the compact disc player is a quantum physics machine. Now, with it, people were able to hear music essentially perfectly reproduced anywhere in the world, on the mountains, in the forests, in the sea, in the deserts. So that's my title, you see. Quantum physics has democratized music. Something people don't know and should be made aware of in this context and in innumerable others where physics is applied. Now, I'm well aware of the complicated history of all inventions. And the CD player was one stage in a long and still continuing process, enabling people to hear music at will. Of course, there was the gramophone. People could hear music in their homes. It wasn't really a portable thing, unless you've seen the wonderful film by Werner Herzog called Fitzcarraldo, where a gramophone is taken up the Amazon to broadcast opera music to the supposedly ignorant people on the riverbanks. But basically, it wasn't a portable device. I can't resist showing you this picture of Emil Berliner. He was a pioneer of the first commercially successful gramophone. Now, my mother's maiden name, unmarried name, was Berliner. And one of my relatives, one of my cousins, wants us to believe that this guy was one of our relatives. I don't believe it. I see no evidence for it, but I wish it were true. But of course, as I said, the gramophone wasn't portable. Then there was the radio. Well, you could hear music in your home, but you couldn't choose what music you were going to hear. And then, of course, some of us will remember the Walkman tape recorder. There you could carry music where you wanted, but the tape was awkward. If you wanted to find a piece of music, you had to search through and so on. The CD player was the first truly portable, convenient way of listening to music. But it's been superseded now. We know that by MP3 players and iPhones, more convenient still. And again, quantum machines, based on transistors, designed using the quantum physics of certain classes of solids. I just chose a CD player just to illustrate the point about connections. Now, here's one of the bees in my bonnet. Okay, I have a strong dislike of the term the real world. It's usually employed, certainly in the UK, and I suspect here too, in a disparaging way to contrast the abstractions studied in academia, people like us, with the world of money. Now, isn't it strange that people would think that money is more real than electrons, atoms, stars, and planets? Ask yourself this question. Where exactly is the money in your bank account? Well, it's an abstraction. It's an essential part of being human that we invent abstractions, money, equations, many things, and quickly come to regard them as existing independently of us, as real, a term, as I said, I dislike. Abstractions are useful tools, part of our humanity, as I say, helping us to navigate with each other and between levels of description in the unimaginably, ultimately complex world, that unknowable in its ultimate nature, in which we find ourselves. Now, of course, there is economic value in quantum physics, and it extends very far beyond the little CD player example that I started with. I read that the high-energy experimentalist and Nobel winner Leon Lederman estimated that 25% of the gross national product of the industrialized world depends directly on quantum mechanics. Other reports gave 30%, another one-third. I wanted to track down the source of Leon Lederman's estimate, and eventually I found the following interview with him. Leon Lederman, according to some absolutely closer to truth testimony that I gave before Congress, quantum mechanics accounts for 37.9% of the gross national product, or some number like that. And the interviewer said, "How did you get that percentage?" Leon Lederman, "Well, I made up the number, but it's plausible. You get it by tallying up what we have thanks to our understanding of quantum theory. Without that understanding, we would never have transistors, microprocessors, the whole microelectronics revolution wouldn't have taken place, our computers wouldn't be what they are, the biotechnology revolution was catalyzed by Watson and Crick's discovery of the structure of DNA in 1953, which was stimulated by a book by Schrödinger on the quantum theory of large molecules. The core products of 21st century technology, this is still Lederman, electronics, computers, biotech, all relate directly to an understanding of quantum theory." And that quotation doesn't even mention lasers scanning our purchases in every supermarket. Elsewhere, he mentioned MRI scans, magnetic resonance imaging based on nuclear spins. What a pity that the medics have deleted the N from nuclear magnetic resonance. I have a sort of single-handed campaign to try to bring it back. It would probably fail. And $5 billion a year, he estimates. PET scans, positron emission tomography, based on annihilation of particles and antiparticles. That's quantum mechanics and relativity. Particle accelerators treating cancer, plastics, diagnostic radiography, $25 billion. I don't know what it adds up to, said Lederman, but it's a great deal. Okay, I want to give you another example of democratization. In October 1833, a young English gentleman, Henry Fox Talbot, was on his honeymoon in Italy. And he was sketching by the shores of Lake Como. This was a common occupation for gentlemen in those days. They fancied themselves as artists. And one eye was pressed close to a camera lucida. That's a draftsman's aid, in which an image of what's outside that you want to is projected onto a piece of paper, and you can draw around it. That's the idea. Now, it seemed very easy to trace the outlines of the villages and the lake and so on, distant mountains, with his pencil. But it only seemed simple because he quickly realized that he was actually no good at it. He recalled later, he said, "For when the eye was removed from the prism in which all looked beautiful, I found that the faithless pencil had only left traces on the paper melancholy to behold." That's his drawing. And when he compared it with the real thing, as he said, when he recalled the inimitable beauty of the pictures of nature's painting, which the glass lens of the camera throws upon the paper in its focus, he thought how charming it would be if it were possible to cause these natural images to imprint themselves durably and remain fixed upon the paper. And after several years of experimenting, he invented the type of photography that we all used for more than a century. Now, the invention of photography, like anything else, is a complicated story. It involves chemistry, common salt, silver nitrate, sodium hyposulfite. Many of you know more about this than I do. And several people. It involves Thomas Wedgwood, Nicephore Niepce, and Louis Daguerre, who's very well known, John Herschel, the astronomer, and Talbot, Henry Fox Talbot. Now, his unique and seminal contribution, none of the others made it, was to invent the negative, the photographic negative. Here's a print from the first negative. And the point of this is that it enables many copies to be made from a single picture. The other people invented sometimes very beautiful reproductions of natural scenes and of people, but only one image at a time. He couldn't print off many. It's the negative. I visited the village, the abbey where Talbot lived. It's not very far from Bristol, where I live. And I took my own picture of that same window today. So it's not a bad picture for 1835. That invention of the negative, of course, enabled people remote from the locations of the original to see reasonable reproductions of works of art and of natural scenes, sculptures, buildings, without visiting them. So it democratized the image. This is chemistry and optics now. Well, that was photography until the 1990s. It was democratic, but only partially so, because you still had to take the plastic film on which you had taken the picture to be developed usually by other people. I mean, you could do it at home, but it was something most people didn't want to do. Well, then came digital, of course, which we all use now, and that completes the democratization of the image by giving us complete control. You know, instead of film, the image falls on a CCD, a car-charged coupled device, and that captures the light using exactly the photoelectric effect, that quantum process that Einstein identified in 1905 in his seminal first paper on the granularity of light. So the digital camera is another quantum physics machine. Photoshop, you know, you can manipulate easily on screen, again using a computer, another quantum physics machine. We can send the pictures by email, or we can print them using inkjet or a laser printer. That's the quantum physics machine again. So the democratization of the image is complete. Now, there's a curious retro twist to this story, recalling Fox Talbot's episode in Como. You can now buy camera lucida apps for iPhones and iPads. Okay. Now then, all this physics-based technology is wonderful. And, as I'll get to presently, not only in the way I've been talking about. But, as Richard Feynman put it in his inimitable way, physics is like sex. It has consequences, but that's not why you do it. Well, why do we do it? Well, we do it to explain things. There are misunderstandings about explanation. One of my students, when I did give lectures on quantum physics, he wrote, "I enjoyed Professor Berry's lectures, but he didn't explain what use quantum mechanics is." Well, I've just been talking about that. It's funny, the student, I mean, I'll tell you another student report. It's curious what they write. This was from a project in which I'd supervised. "Thanks to Professor Berry, who, without none of this, would have been possible." Okay. Anyway, the same student who wrote, it didn't explain what use quantum physics is, went on. He wrote, all right, so it explains things, but they would happen anyway. Now that actually raises deep questions about the relation between the world and our explanations of it. And I sent it to our philosophy department for them to discuss. It's their business, actually. Now, sometimes our explanations seem remote, related only distantly and mysteriously to the phenomena they're supposed to be addressing. As I mentioned briefly yesterday, there's the mythical paper that begins, "Consider a spherical cow." Well, I especially like the beginning of Wallace Stevens's poem, very long poem, inspired by Picasso's picture, The Old Guitarist. He didn't intend, Wallace Stevens, this first part of the poem to be a kind of metaphor or a tongue-in-cheek manifesto for theoretical physics, but it could be. They said, "You have a blue guitar. You do not play things as they are." The man replied, "Things as they are changed upon the blue guitar." Well, that's physics. Now, there's another misunderstanding related to this, associated with the fact that you can have a fundamental theory of some particular phenomenon, or even a theory of everything, but the conceptual distance from the phenomenon is so great that the supposedly encompassing theory has difficulty accounting for it. String theory is a current front runner in this very brave attempt to explain everything. Now, the novelist Ian McEwan made this point, that you can have a theory of everything, but it is not really powerful enough to explain any particular thing in a comprehensible way, in a very clever way. He had, in his novel, Solar, he describes a badly behaved string theorist who, when his wife catches him in the arms of another woman, tries to reassure her, he's a string theorist. "Don't worry, my dear, I can explain everything." I also sent that to my philosophy department, and they spent days deconstructing it. I mean, it raises very deep questions about how physical theories at a higher level of generality can include other theories, as special cases, usually older theories of more limited applicability, but where the older theories can explain something very clearly and the supposedly more general ones have difficulty doing so. It's what philosophers call the problem of reduction. I have a great deal to say about it, but not today. It's another lecture. Except to say that there's a sort of political analog. We're all familiar with ideologically driven people who claim to love the whole of humanity, humanity in general, but in their private lives behave very badly to all the individual human beings with whom they come into contact. Well, Isaac Newton was very well aware of the point that science proceeds little by little, never trying to explain the universe in its entirety in one go. Here's what he wrote: "To explain all nature is too difficult a task for any one man or even for any one age. 'Tis better to do a little with certainty and leave the rest for others that come after than to explain all things by conjecture without making sure of anything." And of course, Newton's credentials were pretty secure in this matter. But still, we do explain. And here's an example I particularly like. It's not from my own work, it's other people. Ask this question: why is gold golden? Well, that's a question about the quantum physics of condensed matter. The color, it's yellow plus shiny, comes from the light reflected by the surfaces, the light that's not absorbed. And the light that is absorbed is the light that interacts strongly with the electrons in the crystal structure of the material. Now, understanding it involves quantum physics. It's a calculation. You can't do it on the back of an envelope, and it wasn't done properly until the 1990s, and you used the Schrödinger equation based on quantum physics. Now, and this calculation did predict the color. There's a relevant pair of energy levels. It's the 5D to the 6S transition, and the energy of this in the solid was calculated to be in the ultraviolet, which of course you can't see, so the reflected light pretty well covered the whole of the visible spectrum, so the predicted color was actually silver. Okay, now that was the best calculation possible at the time, and what was wrong? Well, what was wrong was they missed the fact, very quickly realized, that gold is heavy, so its electrons move fast, and you need relativity, physics of the fast, to be incorporated in the calculation, and that requires quantum relativity. It involves not the Schrödinger equation, but the Dirac equation. Dirac now recognized as the greatest intellect to be born and educated in my city, in Bristol. Well, when you repeat the calculation, the relativistic contraction of the S level, where the electrons are close to the nucleus and move fast, shifts the energy level closer to that of the d orbital and gives absorption in the blue, so that the red, green, yellow reflection that you then get makes the color come out right. So here's a nice fact. Gold is relativistic silver. It's a very unexpected connection, that to explain this color that has so fascinated human beings for thousands of years, you need the two great advances of physics of the 20th century. You need quantum mechanics, you need relativity. Now, it's something to think about. I recently learned a related thing, actually. A couple of years ago, a paper appeared in Physical Review Letters giving the first quantum physics analysis from first principles of the lead-acid battery that you use to start your car. Now, it's a complicated study, and it has to include relativity, again, because lead is heavy, and its electrons move fast. Now, the surprise is, as with gold, you don't get the right answer, but you get a dramatically wrong answer if you don't include relativity. You only get 20% of the EMF, the voltage, that the battery would produce. 80% is from relativity. That's why a tin acid battery wouldn't work. Tin is lighter, it's chemically similar to lead, but it wouldn't work because you don't have this relativistic effect. So just think, every time you start your car, you're using a process dependent on relativity, even when you don't drive near the speed of light. Okay, now I've talked about some examples of technology that wouldn't have been invented without physics, that's a CD player, or chemistry, that's photography. Now, this principle is well understood now. You all know it, and there are many, many examples, a host, innumerable examples. We emphasize to politicians how any investment in science is likely to generate enormously disproportionate rewards, not necessarily, certainly not at predictable times and or particular ways, and not to order, and sometimes only after considerable delays. But we don't usually emphasize an opposite process, how new technology generates new science. Now, all of you here know this if you just walk around these exhibits and see how technology is involved in teaching and how you can do lots of physics using technological machines. Or even new art, by the way. In his book, Bright Earth, the science writer Philip Ball explores in detail how, over several millennia, every development in fabric dyeing or paint technology was immediately adopted by painters eager to exploit new ways of putting paint on surfaces and new types of new colors which were invented by the chemists. It's a fundamental influence of the development of visual art on technology, which is usually ignored by historians of art. Now, all scientists use technology in their research. Of course we do, but we don't often comment explicitly on it. My own research as a theoretical physicist has been transformed in my lifetime by the quantum technologies of computers, lasers, digital photography. I'm going to give just two examples, little small vignettes from research over many decades. I wonder how many of you have seen oriental magic mirrors. These originated in China 2 millennia ago, and they're cast bronze with a polished front surface. That's the mirror here you can see. They're not perfect quality, but they're not bad. Now, on the back of the mirror is a deep relief pattern. Mine has signs of the zodiac on it. And the magic comes when, instead of looking at your reflection in the mirror, you shine a light on it and you look at the reflection, the sun, for example, take it outside, and you look at the reflection on a wall or on a piece of paper or whatever, on a screen. Now, you should see, and you do see, a bright disk of light, reflected light. But unexpectedly, in that disk, you see a ghostly image of the pattern that's on the back. It's as though the mirror's transparent, the light penetrating it and being reflected from the back. It does seem like magic, and it was probably an unintended consequence of the way that these mirrors were made. Of course, it isn't transparent, that's nonsense. And after a century of confusion, following the introduction of these mirrors to the West in the 19th century, it became clear that during the casting and the very robust polishing, the pattern on the back is weakly reproduced on the front, something like that. I've grossly exaggerated it. Not deliberately, but by the elastic release of stresses in a way that isn't actually completely understood now. But this didn't explain the optics. How can it be that a pattern too small to be seen by the eye, when you look at the shiny surface, it looks perfectly smooth, can generate such a clear reflected image as the one I showed you? It isn't an image in the usual sense, because that would involve focusing. It would only come at a certain distance. There's over a very wide range of distances. You get this fairly sharp, ghostly image that I showed you. Well, the answer came from a theoretical analysis revealing a scarcely explored regime of ray optic, geometrical optics, in which the curvatures of the surface relief concentrate the light, but are too weak to bring it to a sharp focus, a kind of prefocal brightening. It's particularly simple theoretically, and the curvature is the slope of the slope. It's a Laplacian operator, for those of you who know that dialect. And there's a precise formula for, given the height of the surface, what the image is. It's a very simple formula. Now, you can test it out. You can take what you observe, and then you can take the surface of the mirror, and you can apply this Laplacian image transformation and get this simulation. And it has a property that is a central feature of this curvature transformation. If you have a surface of steps, up goes to down, the curvature, the image of them, has a bright side and a dark side. And you see that here on every, this is a useless one. On every edge, every step, you see a bright side and a dark side. And that's a conclusion of the theory that's borne out by observation. But with a digital camera, a quantum physics device, as I mentioned, you can do much more. With a computer, that's another quantum device, you can import the image of the data file, and you can clean up one of the edges by averaging along, and then you can actually scan across this bright and dark image of a step, and you can then, using the theory, you can calculate the height of the step. And it's a few hundred nanometers. And that explains why it's too small for you to see, but it's not too small to produce this image that I've described. So that's understood. Now, if I wanted to do this research, let's say 3 decades ago, I would have needed image capturing equipment and image processing software, which would have cost tens of thousands of dollars. 4 or 5 decades ago, it would have been so laborious that nobody would probably have tried it. But now, with ordinary commercial digital cameras, the little digital cameras we've all got, and standard software on an ordinary laptop, theorists like me are liberated to do research of this kind. It's no exaggeration, in this case, that quantum technology enabled the solution and understanding and demonstration of the understanding of a problem that was several millennia old. By the way, this optics is useful. It's a lensless way of testing surfaces, and indeed in some parts of the semiconductor industry, To see if surfaces are flat and free from scratches, you simply look at the light reflected onto a screen. In Japan, it's called Makyo imaging. Makyo is the Japanese for wonder mirror. Now here's a second example. It's very different. In quantum physics, you know, microscopic objects are represented by waves, and the strength of the wave at any place gives a probability that a particle will be recorded there. This fundamental aspect of the world, as I mentioned, was anticipated by Einstein and first expressed clearly by Max Born a bit later. I've said this earlier. Now, it seems very mysterious, a wave of probability. It seems a notion far removed from anything you're familiar with. But it isn't, actually. We're all familiar, unfortunately, hopefully only by reading, with a crime wave. Now, what's that? That's a wave of probability. It passes over some region of a town or whatever, and giving the probability that unfortunate events will take place, but without specifying exactly where or when. Of course, quantum mechanics has other differences, but that aspect, wave of probability, is something we're familiar with. Now, sometimes the quantum waves are concentrated into pulses called wave packets. Okay, and they travel in waves which are a bit reminiscent of the particles of Newtonian physics. Experimentally, you can make these localized pulses in an atom by zapping an isolated atom with a laser and sending one of the electrons into a very distant excited orbit, in which it goes round and round this pulse, isolated pulse, like a Newtonian particle would. But there is a difference. In these, they're called planetary atoms, the electron waves, unlike real planets, soon spread to fill the entire orbit. You get spreading of wave packets in a ring of probability. But about 20 years ago, it was realized by theoretical analysis of quantum equations that there's a more surprising difference. After a very long time, this spread out wave packet will reconcentrate itself, reviving the original localized packet. And not only this, the process of spreading and reconcentration occurs repeatedly, a series of quantum revivals occurring at multiples of this revival time. Now, the quantum equations describing this look complicated, and they are complicated. But with computers, quantum again, we can bring quantum mathematics to life as pictures. Now, this is not always appreciated. You know, there's a cliche, you know it. A picture is worth 1,000 words. But it's nevertheless true that an equation is a more economical representation. It summarizes infinitely many pictures. But economy and worth aren't the same thing. And with the extreme compactness of equations, there can come, as we all know, a loss of comprehensibility and immediate understanding, and pictures can remedy this. Now, not every scientist has a visual imagination. Here's the abrasive but much loved Wolfgang Pauli, who was called the conscience of physics, skeptical about pictures created in the early days of quantum physics by Henrik Kramers to illustrate waves inside atoms. Our good friend Kramers and his colored picture books. Children, they like pictures. The desire of children for visualizability is reasonable and healthy, but still, such a desire in physics can never be an argument for maintaining a particular system of concepts. Now, it's true, a picture is not an explanation, and it doesn't compel any particular system of concepts, but it does help us discover phenomena and test explanations. I'm going to illustrate these quantum revivals, not with atoms, but with a simpler situation of particles bouncing back and forth between parallel walls. Now, when we teach quantum physics, we call this the particle in a box. It's a simple little mathematical model, to some extent realized now with quantum dots and the like. Here's what a particle would do in classical physics. There it is, and I want time going upwards and pictures going, space going sideways. And of course, you know, it moves and it bounces and it moves and it bounces, and that's all there is to it. It keeps on doing that. here's the quantum equivalent of that. There it is as a wave packet, and you can see that it bounces and it interferes with itself because it's a wave, and it gradually spreads. Now, this is only a very short time. It's a classical time, but it's 1/20th of the very long quantum revival time. And so here you see this bouncing and interfering and spreading. Well, now there's a further richness that I didn't mention so far. Theory predicts that between revivals, at fractions of the revival time, let's say a third or a half or something, the wave reconcentrates onto several copies of the initial state, 3 or 2, depending on a third or a half or whatever. Now, sometimes these fractional revivals are described as the electron being in several places at once. You've all read this. It's a kind of absurd thing. I don't know why people persist with this terminology. It's just a confused way of saying that the probability of finding the one electron is divided in several places. I mean, imagine someone wanting to contact me and knowing that I divide my time randomly between my home and my office. He or she immediately understands that I'm not split between two places. It's just the probability of finding me is split between the two places. Okay, well, here's a 2 split. Okay, and this is it's the middle 1/20th, between 9/20th and 10/20th, a half of the revival time. And you see out of the mess there come these two probability maxima of the electrons. Okay. It's nice to see, and it's slightly less obvious than what I first showed you, but the true value of recommending mathematics pictorially comes when you look at the complete picture over the whole revival time, called a quantum carpet, showing the whole development. And here it is. Now, this quantum carpet, it requires extreme coherence, and only certain parts of it have been seen experimentally, but everything that's been checked works out. But look, down at the bottom here is what I showed you at the beginning, this first little bounce and spread, but then it gets complicated and you get the 2 split in the middle and so on. Now, there were many features that we saw when we did these calculations, which we hadn't anticipated, particularly these diagonal lanes, and it took quite a bit of explaining. So, quantum physics, that's my computer with its transistors, helps me to understand quantum physics. Okay, these repeated revivals and subtle phenomena associated. Now, related to this is another example of my underlying theme of connections. We theoretical physicists are never more delighted than when we find that something we've developed, some theoretical or mathematical explanation to explain one phenomenon, works precisely in an area that we thought was very different. The physicists who studied quantum revivals for electrons in the early 1990s didn't realize that the phenomenon is mathematically identical to something discovered in optics in 1836 by the same Talbot who invented this photography in the negative that I've mentioned. He was experimenting with light transmitted through a fine grid, what we call now a diffraction grating, umbrella material or net curtains, and you're all familiar with diffraction gratings. You look at the distant light through a net curtain, and you see it split up into a number of different spots. And of course, you know that if the light's replaced by X-rays or neutrons, this gives you a technique which has been central throughout the 20th century, since 1 century ago almost, when the Braggs and the von Lauer first developed the theory and understanding of it, as an essential diagnostic tool for understanding the structure of material in modern microbiology, DNA, for example. Now, Talbot noticed that instead of looking in the far field like we do in X-ray diffraction, you look near the screen at different distances from the grid. Of course, at the grid itself, you have a sharp image of the grid. Then it gets blurred out by diffraction. But at a certain distance, the pattern reconstitutes itself, and you get a repetition. And at multiples, again, a repetition of the pattern. Now, he guessed that these repetitions had something to do with wave interference, but the full theory wasn't developed until the 1990s. Now, these formulas for Talbot repetition at successive distances are identical with those for quantum revivals at successive time because of a known similarity of the underlying wave equations.